You started the recording. So hi everyone. So yes, we will present you this paper we had on the Bayesian workflow for disease transmission modeling in Stan. This was a very collaborative work. So with there are four of us: Léo, that is at INREA now doing a PhD; Charles Margossian, that is at Columbia University; and Lisa, that is at Imperial. And I am from the University of Bern. And so we will share the presentation in three parts. I will start with a bit of introduction about transmission models, and then we will have some more hands-on tutorial of how to do it really in Stan and a few more examples. So the objective of this presentation and this paper in general is to show how to fit a simple transmission model in Stan. And it's based very thoroughly on this paper that is linked here. And the prerequisites are just basic programming with R that I think are probably good for everyone, and a general understanding of Bayesian inference, which should be something that everyone here has. And as you said, the material is all on GitHub. So the outline is first models of disease transmission. And this is a topic that probably not everyone is familiar with. So we thought we will start with that. So we have there are a lot of different classes of models of disease transmission. And you can think of them as having different characteristics. So the first characteristic that we care about to differentiate these models is interpretability. So you have some models that are only phenomenological, and the other are more mechanistic. So you can interpret the value of the parameters to have some meaning in real life. That's what mechanistic means. We have also the scale of the model. Some models are population-based, some others are more agent-based. We have also the framework. Some models use deterministic frameworks and others stochastic. And you have also a lot of different data generating mechanisms that can be included or not in the model, like incubation, contagion, immunity, vaccination, mobility, etc. And in the case where you want a mechanistic model that is population-based and deterministic, generally people use frameworks based on ordinary differential equations. And that's what we will talk about today. This is like the basic models that people use in infectious disease transmission. So these ODE-based models, when you do that, you just a quick introduction, really. You have to divide the population into homogeneous groups that we call compartments. Then you define the flows between the compartments with ODEs. You define the initial conditions, and then you solve for the time-dependent volume in each compartment in time. If you start with a very simplest of the models that people use, is a susceptible infectious recovered model, SIR. And it is basically like that. You have like this, you cut your population in three. And then you say that people go from susceptible to infectious with this flow, and from infectious to recovered with this flow, and then you have it. So if we dig a bit more into this, the SIR model, you have, so S in time is the number of people susceptible to infection. I is the number of people infected, like the prevalence. R here is the number of people recovered, and here you assume that they stay here, they stay recovered for life, basically. And then you have the total population size, which is just the sum of the three. And you have these two parameters that determine everything in the model, which is beta here, the infectious contact rates per day per person, and then gamma, which is the recovery rate. And the recovery rate corresponds to 1 over the infectious period. So the intuition behind this SIR model is like the high T over N in time is like the proportion of infected, so like the prevalence of infection. If you multiply this by beta, you get the daily number of contacts with infectious people. And then each day, you can say that beta Si over n, people become infected. And this is called the force of infection in the classic formulation of the SIR. And in the SIR, you have a few assumptions, which is like homogeneous mixing, which means that you are as likely to mix with everyone in population. So you have like people that are susceptible become infected, and you assume that this rate is like homogeneous. So everyone in the population is equally likely to meet and to get infected from everyone else, which is a rather strong assumption and doesn't work all the time, obviously. You have beta and gamma that are here constant over time, which means like in transmissibility is constant over time, which is also often not true. You see that all infections are observed, which is also not true in many cases. Here, there is no incubation. Because we use OD, we assume that the recovery, the time spent here is exponentially distributed. And as I said, you have this lifelong immunity and stable population. Nobody is getting born, nobody dies, everyone goes from left to the right and stays here, basically. But this is the very simplest version of the model. So the point that I wanted to do now is to show you quickly how to simulate the SIR in R, and that will make the basis for later when we try to fit the SIR in Stan. So we have this library that everyone uses, dsolve. You can just create a function. I assume everyone is familiar with R here. So you can just write as a function the system of ODEs that I showed before. So you see ds, di, dr, beta si, beta si, gamma, etc. So it is really straightforward to do so. You can try it yourself. Then you select the value of the parameter. So let's pick beta 0.8 and gamma 1/7. As I said, gamma is 1 over the infectious period. So it means like you assume that on average you stay 7 days sick. You are sick for 7 days here. And you have to set the initial values. So here I just put 100,000 people, 50 infectious people at start. And then you can just compute the initial values for every compartment. So 50 will be here. Everyone above 50 people will be susceptible and nobody is resistant. And then you can just solve it quickly with the ODE function in R from the dsolve package. And you will just get this in time. So for every time you give from 0 to 50 here, for every time you give, it gives you how many people are in each compartment. So this is really straightforward to do. So, and what I did here is to add a bit of intuition of what the different values for the parameters mean. So if we pick, like I said, 0.8 for the beta, 1/7, and then this number for the initial conditions, you see that basically people will get infected in like one big wave. And after a while, it will stop, and everyone, basically, most of the people will be in the recovered thing. But if you just increase the beta, so you put it at, for instance, 1.1 instead of 0.8, you see that the wave is actually steeper and a bit earlier. It comes quicker. It's the dash line here. So increasing the value of the beta makes the wave come sooner and be like harder, basically. And if you put the beta at the lower value, it will be a wave that comes a bit later and that's flatter, which is like flatten the curve thing, you know. So actually at the end, you will have the same number of people infected in total. Basically, everyone will get it, but at a slower rate. This is just the intuition behind it. And if this time you change the gamma instead of changing the beta, so if you make the gamma 1/14 instead of 1/7, which means that you say people stay infected for 14 days instead of 7, then you see that in that case you will have a shift toward higher. So you have a bigger wave that comes at the same time. And if you make it shorter, the infectious direction shorter, it will go the other way. So it's a bit to show you in every direction the thing moves. If you put the initial number of people infected to 500 instead of 50, you would just have the exact same shape, but shift it to the left. And if you put 5 people instead of 50, you would have the exact same sheet it was right. So I think it's good to understand that when you look at data, for instance, a COVID wave or anything like that, to understand what do the parameters do actually in what you do. Yes. So the applications of these compartmental models, you can use them for many things, and especially for COVID, many people use them for many things. The first thing is to get just mechanistic insights about an epidemic. You can have like transmissibility levels or not. You can have the drivers of transmission. So it's more understand what's happening, and from there, so often you can formalize and put numerical values on general concepts like herd immunity. How many people will need to get vaccinated before we can control this? It is general. It's not really predictive or anything. It's more like in general for on life. You can understand that. And then you can also use these models, maybe not the simplest SIR, but these kind of models, to produce forecasts, mostly on the short term, because it's always difficult to go a bit longer, but you can have short-term forecasts that account for contagion and immunity. But all of these things that you can do with these models, they are used on the numerical values of beta, gamma, and all the initial conditions, and most importantly, the uncertainty. And this is where a bit Bayesian inference becomes really important, and that's where it goes into the problem of Stan and everything. It's like you can infer the parameter values from data, integrating the data and the domain knowledge under the form of the priors. You can be also more efficient for complex model and high dimensionality. You can use a lot of things like that and understand more thoroughly what's happening. And with Bayesian inference and Stan, you can quantify and propagate the uncertainty in parameter estimates and propagate them into the forecast if you want to do that. And for that, we argue that one of the best way to do so is to use MCMC and Stan. And this is why we basically started with doing this tutorial on how to do that in Stan. And so at this point, I will leave it to Lisa that will start with the Bayesian inference with Stan and how to fit these models in Stan. So Lisa, if you want to share.
Can everyone see my screen now?
Yeah.
Yes.
Excellent. So yes, how about Bayesian inference? Now we understand what the model is, what we want to model, and what parameters are important. But in a real life situation, we don't know the values of those parameters. What we do have is some observed data. So this is Bayesian meetup. I assume every single time you see this formula, but just to recap. So what we start with usually is a belief about the unknown parameters theta, we call them prior, and also we decide forth some likelihood, and by likelihood we understand the data generating process. So for instance, now we have assumed that the data generating process follows the ODE. And this will be the part that will allow us to link the model to the observed data. So the product of prior and likelihood define the joint distribution of data and parameters, and it will allow us to find the posterior of the parameters given the data. So let's consider a simple case. Now, based on the Bayes rule, what we need to specify, we need to specify a prior, and we need to specify the observational model. So in this simple example, we have a set of observations, y1 to yn, which are governed by an unknown parameter theta. We assume that all these observations are distributed normally and they are all independent. So normal IID with known variance of 1 and unknown mean theta. So the observation model is then defined by the likelihood as presented here. So since we have made the independence assumption, the whole likelihood can be written as the product. And we give prior also to this unknown parameter theta, for instance, normal distribution. So what we would like to find now is the posterior of the parameter theta. And here's where Stan would help. So there is loads of MCMC algorithms out there in the nature, and also other inference algorithms. Some of them approximate, some of them exact. But as practitioners, we don't need to worry about that. And I know it might sound as an oversimplification, but what we need to know well is how to press this inference button really well. And by pressing inference button, we mean using a probabilistic programming language such as Stan. So again, to be able to formulate a model in Stan, we need to be able to specify the data generating process, to specify the priors. Stan itself is written in C++, so Charles Margossian is one of Stan developers, is on the call here today. And what's behind Stan is the Hamiltonian Monte Carlo algorithm, an algorithm that belongs to the MCMC family. And very important features of modern Stan is also that it supplies us with great diagnostic tools. So we can not just press that inference button, but we can also evaluate the quality of that inference by using the diagnostics, which are already pre-built. And also Stan has interfaces to different languages, R, Python, Julia, MATLAB. How does a typical Stan program looks like? So most of the programs will have sections such as data, parameters, and model. And some of them would include more. So here is an exhaustive list. Disclaimer, I think in the paper, we have a graph of all these blocks, and I think we forgot the function section. So before everything comes the optional function section, where we can predefine some functions which will be reused in the body of the remaining code multiple times. Or maybe it's useful to separate that code for logical reasons. Data section speaks for itself. So here we specify which inputs we provide to the model. Transformed data block allows us to either specify some additional fixed values or also perform some transformation on the input data. In the parameters block, we declare parameters of the model, including, for instance, very important, the constraints on the parameters. In the transformed parameter section, we are able to transform the declared parameters. For example, this is where solution of an ODE would happen. In the model block, we define the price and the remaining part of the data generating process. So the model section is exactly that section where the joint probability is defined. Generated quantities block does not have any influence on the MCMC algorithm. It is rather a section which helps us with certain other tasks, such as when we would like, when we're working with predictive models, when we would like to make prediction on some unobserved data, so on the holdout set, generated quantities block would work perfectly for that. Or when we would like to create some quantities such as R0, the basic reproduction number, again, This would serve us really well, or also for posterior predictive checks. And also for model comparison, we can make the calculations here so that we can use them after we have run the model to compare models. So let's go back to that elementary example. Nothing about ODEs now here. All we have is the IID normal variables. And to run such a model, we would only need 3 blocks. That's data block, parameters block, and model section. In the data section, we of course need to say how many observations we have, and then provide the array Y with the pre-specified number of entries. Then in the parameters, we declare the only parameter that we are going to infer. And in the model, we specify the prior for theta as well as the likelihood. There is an alternative way of expressing this. For instance, we could write target plus equals and then write the log probability. So once we have formulated those blocks into a text file, we save it under, for instance, model_linear.stan. So that's a file with the extension .stan. To run this, so now is the time to press the inference button. And when we're using our interface, we can use one of the packages that allows us to do that. For instance, rstan. And the next section, we generate some data where we know the true value of theta, that's 0.7, and we simulate 50 observations like that. And then we collect all the data for Stan into a list. So in the model, we have said that we will provide Stan with 2 data inputs, that's N and Y. So we put them into the list, and then we run the Stan command with, as we chose, 4 chains and 1000 iterations. After we have received the output from Stan, after we have received the StanFit object, we can then evaluate visually whether the results are reliable. So what we are seeing now is a trace plot obtained from 4 chains and 1000 iterations. So there are 2 areas now, the shaded area to the left and the not shaded area, the post-warm-up area to the right. What we usually want to see on a trace plot is stationarity. So we would like to see 2 things. A, that each chain's the draws in the non-shaded area, that each chain in that area agrees with each other, so it looks stationary, and that different chains agree between themselves. So stationary means that if we chop the chain into several pieces and we interchange them. So for instance, if we chop it into 2 pieces, 1 and 2, and then we make 2 become the first part of the chain and this first become the second part of the chain, visually those 2 different versions of the chain should be indistinguishable, because this would mean that the chain has reached a stationarity. This is a bad example. This is a type of output that we wouldn't like. So imagine now we cut these chains in half somewhere at iteration 500, and we change the 2 halves of the chains. And definitely it would not look same. So the chains don't agree with each other on a big range of iterations, but also each chain itself is not stationary. Another visual check that's good to run when we have several chains available is whether posterior distributions from different chains agree. So when we plot them one over each other, they should roughly overlap. Just by printing that StanFit object, we already can also see the quantitative measures of convergence, so the quantitative diagnostics of convergence. And most importantly, we'll see the estimated values of the Gelman-Rubin statistic and the effective sample size. So roughly, the Gelman-Rubin statistics does exactly what we're visually inspecting on the trace plot. So roughly, it is the within chain to between chain variation, and effective sample size will tell us if we had all the draws in the MCMC independent, how many of those draws would we need? Because now all the draws are not independent, so we need a higher number of those as compared to when the draws are independent from each other. So now we know what model we want to encode. Now we also know how to encode models in Stan. And it is time to encode that specific SAR model. So the first example we begin with is using publicly available dataset in the package outbreaks. This dataset contains the daily number of cases for 14 days straight of an influenza outbreak at a British boarding school in 1978. So in total, the boarding school has 763 students, nearly all of them full boarders. And during the course of the outbreak, 512 of the boys became ill. So you can see the plot of the raw data. And this data represents prevalence. So on each day, we have access to the number of infected individuals. And so now we begin to think, how do we formulate this model in Stan? What are the inputs? So again, we have prevalence data, then also we have fixed parameters. We also know that the outbreak started with one infected individual. That's why our initial datum is I0 equals 1. Then recovered, we have 0 number of people because no one has been ill yet. And the rest of the population is susceptible. The likelihood that we choose is negative binomial. Why? Because we're dealing with count data. So our choice then is between a couple of count distributions. Negative binomial is more flexible than, say, Poisson because it allows some overdispersion modeled by parameter phi. So now the initial SIR model had 2 parameters, beta and gamma, which characterize the transmission rate and recovery rate. But now also additionally, we have one more parameter phi, which characterizes the likelihood. The next step is to choose some prior distributions on the parameter. So there are, of course, a lot of ways how we can come up with prior distributions in terms of influenza. Influenza is a well-studied disease, so we might just look up in the literature what are the typical values for recovery time. And here, for instance, we put the prior not on the gamma itself, but on its inverse. So if gamma is a recovery rate, then the time that a person spends in the infected compartment is 1 over gamma. And we do have information from the literature about that time. We also need to place some priors on beta and phi, and we make some initial guesses. Here, though, as it has been said, I think on your meetup multiple times, priors can never be understood without the likelihood. So this is a great example where each parameter of the model, of the epidemiological part of the model at least, has a very clear meaning in real life. So placing priors also has some meaning in real life. So what follows next? is the presentation of the ODE signature as we used it, as it existed when we were writing this paper. Also, just bear in mind that now there is new interfaces to ODEs available. I will mention them in one slide briefly. Let's look at this signature as it existed. So now we need to specify in the functions block. So not each Stan model will have functions block, but once we are working with ODEs, it's really convenient to separate the ODE from the rest of the model. And this is where and how we formulate it. So the signature here is that we need to provide the state at time t. So the state is encoded in the array y. Then in the theta array, we will pass the parameters which will be involved in the ODE. Then the x_r, we will provide all variables which will be used in the ODE which are of real nature, and x_i, we will provide all variables which will be used in the ODE which integers. And then having those y, theta, xr, xi, we extract out of those arrays the values which we need. So we extract the initial state of the SIR compartments, as well as parameters beta and gamma. Then we encode the rates of the ODE. These are the last 3 lines. So they are the intuition of any ordinary differential equations of first order is that we provide the rate, so the speed of change of the volume of each compartment. And what we return are the derivatives of each of those compartments. And now let's use this function. So we provide as data initial state y0 and the times ts for which we're going to run our calculations, and number of cases for each of the days. Then in transformed data block, we are specifying just the number of the boys in the boarding school, which is the total population. The parameters now, as we have said, beta, which here in the parameters block is the time to say that we want beta to be bounded from below at 0. Same for the recovery time. So recovery time is the inverse of gamma, and same for the overdispersion parameter phi. Transformed parameters block, as mentioned, is a good place to solve the ODE. So just to mention that it's not mandatory to solve the ODE here. Of course, we can do it in the model block as well. But if it is possible to keep the model block clean and just specify prior and likelihood there, that is great. And that's what we are doing here. So we are calling the ODE solver here, one of them. So at the time, there were 2 ODE solvers available in Stan. We chose one of them to try out. What we provide is the SIR, that was the name of our function where the ODE was formalized. Then initial data, y0, t0, ts are the times for which we're going to run the ODE forward. Theta, the set of parameters, xr is I as specified. So it is very important for ODEs to watch the signature and to make sure that all dimensions are correct. And so, yeah, as I mentioned before, there were 2 solvers, ODE RK45 and ODE BDF, one of them for stiff systems and the other one for non-stiff systems. So now there are other interfaces available as well. So ODE items and 3 of them with tolerances. Maybe Charles can say a word later about them. So, okay, finally, we are in the model block and there is not much left to specify it here. We've done all the hard work already. So we're specifying 3 priors and the observational model. So how actually do we link the cases which we observe to what comes out of the SIR model? So on the SIR model, let's remember we have 3 compartments: susceptible, infected, and recovered. And the infected compartment is exactly what we need. That's the number of infected individuals on each day. So the generated quantities block, as said, is not mandatory. And this is a place where if we want to, we can calculate R0. Alternatively, of course, we can run the model, extract the posteriors of beta and gamma, and calculate R0 already in R. So in summary, again, here's an overlook of all the blocks and what they are used for. Now we're going back to R, creating the list of data inputs, and then run the Stan model, pressing the inference button, and looking at the diagnostics. So we have not seen any divergences and no other warnings from Stan. Great, means there were no problems at the inference stage. Also, we can see roughly in the post-warm-up stage, roughly how our trace plots look stationary. Also, when we overlap the posteriors of different chains, they look fine. And finally, we can run the posterior predictive check. So we have now estimated all the parameters, and using those posteriors, we can run the predictions forward and see if those predictions agree with the observed data, and they do. Here, now we have estimated the R0 value. And as Julien has mentioned, the SIR has used a lot of assumptions, which, for instance, the COVID would not adhere to, and many other diseases would not adhere to as well. And now a bit stepping back from the SIR model, just talking about the iterative process of model fitting. So this process now has been so simple because the data is simple and the disease dynamics is also quite simple. But in most cases, it won't be as smooth because we will have to deal with incomplete data, or we won't have such good prior knowledge about the parameters. And of course, there will be a lot of parameters that we just don't know much at all. So the usual boxes loop in Bayesian case can be expanded to slightly more steps. So we start with building the model, and then we criticize the model before we see the data. And we usually do the prior predictive check at this stage, just to understand whether the priors which we have chosen do cover the reasonable range of the data which we're going to observe. Because also in the cases when we transform raw parameters, it's sometimes we don't have a good intuitive understanding what are we able to encode. So after the prior predictive check, we can go back to the model, then add the data, fit the model, and then criticize the model post inference. And if something goes wrong there, for instance, if we do have divergent transitions, then it is time to go back to the model and revise either the data generative process, or maybe there are simply errors in the code. So main thing, it is an iterative process, and it is important to criticize the model both before it sees the data and after it sees the data. prior predictive checks, as mentioned, is a great tool. So we can either use exactly same Stan code, or we can create a copy of it and just remove the data block and run simulations forward. By running the prior predictive check, we can visualize priors, then to see, okay, I had some raw parameter and then I transformed it. Does it cover a reasonable range of values? Also, we can then overlay the data with the prior predictions to see whether the data lies within the range of predictions, or we have excluded the real data from that area at all. And technically, so as I mentioned, either we can use the same Stan code and just either switch on and off the likelihood, or we can create the copy of the code and remove data and likelihood from it. Here is the prior predictive check for our discussed model. And we can, so how we're doing it, we're generating loads of trajectories forward, and then we can either visualize individual trajectories or a credible interval. So these are the individual trajectories, and these are the credible intervals. When overlaid with observed data, it looks like the priors do allow for the observed data. So our priors are fine. Another way is to use a simulation study. So when we start with our model and we pick some values of the parameters, and then we try to fit the model to the data generated from those fixed parameters. This is linked to the simulation-based calibration when we would do this iteratively many times, but even doing it once already gives some sense of whether our model is adequate or not. For example, if we take this SIR model, we fix models beta, gamma, and then pass these data, the simulated observed number of infected individuals per day. If we pass it to Stan model and run inference, what we should be able to recover are the values which are close in some sense to the original ground truth values. We shouldn't expect, though, that that the values would exactly coincide with what we started with. If we are doing it just once, then the value should be adequate, at least. So after fitting the model, we also perform posterior predictive check. So similar to prior predictive check, but already now when the parameters have been informed by the data. So here is that exact example when we used simulated data. So we can see that values of beta and gamma are very close to the center of posterior distributions. Fine, not so close, but it is still fine because we've done it just once. As said, if we would like to understand better or be able to characterize the system better, the way to go is the simulation-based calibration. And now I pass it to Léo.
Maybe we can do a short break for our questions before the next part, if anyone has some questions.
Yeah, you can use the raise hand function and just ask if you have any questions, or while people think about questions, I have a question, and it regards using the differential equation solver, like or generally using differential equations with Bayesian models. Like, it's something that I don't do quite a lot, so I don't have so much experience with it. So I would be interested to know how easy it is to get the model to converge, and also how difficult, like what are the main problems when using differential equations that don't allow the model to converge? So that would be my question.
So maybe let's start with some elementary answers, and then I think Leo's part will be an excellent answer to this, actually. So your question is a segue to his part.
Okay, great.
So yeah. First of all, as always, with any model, whether ODE-based or not, we need to understand what we are doing. So for instance, if we know that the system is non-identifiable and it occurs in ODEs very often, then no power of MCMC will ever help us. So first of all, we need to understand the system analytically, at least to some extent. So now we said the SIR, this is what it is, and we know what it is doing. Then, as always, priors, even in simple pairs of likelihood prior, it's not always easy to understand what the model is doing with this prior, so how this prior exactly is going to impact the posterior. And of course, in ODEs even further, because each of our parameters does go through some transformations then. And yeah, so prior to trying to get the model to converge, prior predictive check probably should be a step that no one should avoid while fitting ODEs. That's some elementary comments, but maybe let Léo show his part, because he'll going to answer a lot of those, and maybe he can comment as he goes.
Yeah, Lisa, maybe I can make one or two
sure, yeah.
high-level comments. So, and this is a topic that actually is active research. I think ODE-based models are harder than your typical models, oftentimes, because you need to run a numerical integrator, and those are computationally intensive. So if you're using an ODE-based model, you can expect running MCMC to be computationally intensive, right? That's the first thing. The second thing is, in a Bayesian context, whether you're sampling from a posterior or prior distribution, you're actually dealing with a range of parameter values, which means you need to solve the differential equation across a broad range of parameter values. And across that range of values, the behavior of the differential equation can change a lot. And it can be that for some parameter values, it's very difficult to solve the differential equation, right? Whereas for other parameter values, it's easier. So that adds to the computational burden, but it also raises a question of how do you tune a numerical integrator, not only to work for a particular parameter value, which is what a lot of the literature on differential equation is concerned with, but to work across a broad range of parameter values, right? So those are, particular challenges to solving of these in a Bayesian context. Okay, great. It's a very nice answer. Oh yeah, sorry, yeah. But it's doable, and just to be clear, there are challenges, but it's doable, and people do it a lot, right? So, it's one of those challenging things that people still tackle. So I think Dominic also has a question.
Yeah, my question is, because you mentioned one of, I think it was the first or second slide, agent-based models rather than differential equation-based models. I'm sort of struggling to. Can I use an agent-based model? Because I don't know how I get with an agent-based model. I wouldn't have a likelihood, would I?
You could have a likelihood. The problem we have here is that you would have a stochastic event most of the times. So you would like randomly make your agent do something, And when it's not deterministic, but maybe Charles can correct me, when it's not deterministic, it's difficult to enclose in these kind of MCMC frameworks, right?
Can I take this question?
Oh, you can. Sorry, Lisa, please.
So population-based. So what's simple here? We said the whole population is subdivided into subgroups, right? Agent-based. It's more normally they are rather simulation-based models, right? So we would need to simulate forward dynamics for loads and loads and loads of agents, which is possible. Just then, again, I don't know how computationally possible it is in Stan. So now when Julien was showing his example was, I feel like 1 million total population volume. So we would want to simulate 1 million particles. And yes, we can use likelihood when we just say at a certain slice, at a certain time point, we see how many infected individuals we have, and we see 17. So we can still use likelihood. It's more, the difficulty would be in the number of particles. So we would need very many particles to simulate it forward.
Okay, I'm struggling to see how I'd write down I've worked with complicated models for tumors, agent-based models. I mean, there's probably maybe thousands. We're talking about thousands of cells making up the tumor.
So in this case,
I'm struggling how I'd write down the likelihood, because I don't have I just have agents interacting with each other, so I'm sort of struggling a bit. But anyway, I don't want to.
And then the same. So on a certain day, we just sum up. Where our aim is to get the same number, their prevalence. So the number of infected individuals on day T, and that is the sum of all. So we are slicing the whole population and finding that total number of infections on a certain day. And that's exactly the same what we have for our model. So we say this number is distributed with certain likelihood that we
Okay. My problem would be I'd have to take my existing tumor model and rewrite it in Stan, I guess, which would be quite an undertaking, really.
Yeah, so 2 comments. So one of them, I think, generally, writing likelihoods, you probably need to do it by combining a lot of conditional distributions, which I think can be a lot of work. And then the other issue is, I think in an agent-based model, if you write that likelihood, you would end up with a lot of discrete parameters.
Yeah, probably.
Missing variables.
Yeah.
And Stan's main inference engine is gradient-based.
Right.
Hamiltonian Monte Carlo. So that means that you cannot, even if you were able to write down that likelihood, you wouldn't be able to directly apply one of the gradient-based algorithms that's supported by Stan.
Yeah. Okay.
And so usually the work around that. So that's a very clear limitation of HMC. And so so then it gets into questions of, can I somehow marginalize out these discrete parameters either exactly or approximatively? Right?
Yeah.
Or can I come up with a continuous relaxation of the system, right? Which is what is done when you study random graphs, right? But that's already, a whole load more of work.
Yeah.
And say implementing an ODE-based model. So yeah, I definitely think agent-based models come with their share of challenges.
It sounds like it, yeah. Thank you very much.
But that said, not challenges we're not willing to investigate, right?
Good. No, thank you very much, and both of you, for the answer. That was very helpful.
If there are no other questions, I'll move on to my part. So in this part, I'll present a practical example of how to put into application the Bayesian workflow on COVID-19 data. So we'll try to build a model step by step, so to better understand each building block of the model and to understand each issue when they come up. And so here is the data we'll be using for this model. So for each day, we have the number of new cases of COVID-19 in Switzerland in 2020, so from February to June. And so we want to build a model step by step. So we'll start with the simplest model we can. So we just take the SIR model that Lisa presented for the influenza case and try to fit it on our data. We just need to change a small thing, is that in the previous case of the boarding school data, we had prevalence data, which means that for each time we had the number of people currently infected with the disease. Whereas right now we have incidence data, that is the number of new cases each day. And so we just need to change a little bit the model, and we say that we compute the incidence as the number of people going out of the S compartment, so the susceptible compartment, into the I, so infected compartment. So this is what we write in the transform parameter block. So this is the Stan code. And once we have this new parameter incidence, we can use it in the likelihood. And so we use the same likelihood as in previous example, so negative binomial, with as an expected value this new parameter incidence. And for the priors, we just use the same prior as before because we had chosen very weakly informative priors. So as a first try, it should be okay. So once we have done this, we just hit the inference button and see what happens. And Stan actually gets very angry, and we have a lot of warnings. And the most worrying warnings is that our hat is way above 1. So it means that our different chains are not mixing. So again, so we have 4 chains. It means that we run the inference from a different starting point, and we want to see if the chains are mixing. This means that if all the chains are exploring the same posterior distribution after some time for convergence. Sorry. And so when we are such a big R hat, it means that our inference hasn't converged because each chain is exploring a different region in the parameter space. And so for curiosity, we can see the prediction inferred by each chain. And we can see that, for instance, for the reported cases, so this is a posterior predictive check, we can see that the prediction for reported cases are orders of magnitude off compared to the true data in white. And for some parameters, we can see that different chains are actually exploring very different regions of the parameter space, for instance, for beta. So why does our model work so badly? There seems to be an incompatibility between the model and the data. So why? Maybe it's because we put some prior, which is incompatible with the data. But as we put very uninformative or weakly informative priors, this seems quite unlikely. And what is more likely is that we're missing some crucial parts of the true generating process in our model. And so the first thing that can come to mind is that we're missing the underreporting part. Because in the previous example from the boarding school, this was just some case in a boarding school, so we had access to all the cases. Whereas for COVID-19, especially at the beginning of the pandemic in 2020, a lot of infected people were not reported as infected. So we add a new parameter to the model. So this is the block, different block in the Stan code. So you can see that we add a new parameter P reported that we constrain to be between 0 and 1 because it's a probability. And so then we just need to change the transform parameter block. So we just multiply the incidence we computed previously by this new parameters P reported. And then the last part is just to add a prior to P reported. And we add beta 1, 2 prior, which just means that we're very uncertain about the value of these parameters, but we just know that it shouldn't be too close to 1. So this is how you add such parameters to a Stan model. And now we just run the inference again. And so this time the inference seems mostly correct because there is no Stan warning. So we could check a little bit more, but the inference seems mostly correct. But if you recall the drawing for the box loop, for the Bayesian workflow, so after checking the inference, the next step is to check the model, the fitted model. And here we can see that although the inference seems correct, the model predictions are not correct at all. And you can see that, so this is a posterior predictive check. You can see that what, with the value inferred by the model, this is what, in yellow, this is what the model predicts for the number of new cases each day. We can see that the peak is much higher, that the data is skewed to the right. So there is a mismatch compared to the true data. So this means that, again, we're still missing some parts of the true data generating process. And another part we're missing is that for COVID-19, as for most diseases, I think, when you get infected, there is some times before you become infectious. And this can change the dynamic of transmission quite a lot. So we move from a SIR model to an SEIR model, where E means exposed. So it means you have been infected, but you're not yet infectious. So this adds a new parameter, so A, which corresponds to the inverse of the mean incubation time. So we just add these new parameters to our model. And for simplicity, we consider that it's the same time from infection to report and from infection to infectiousness. So we just have one more parameter. So in the function, in the SIR function that Julien had presented, we just add a new line. No, we just add a new term, which is the A times E. And so we just need to add a prior to this new parameter A, and we put a normal 0.4.5, which is quite weakly informative because it just means that most of the probability mass is between, for the incubation time, is between half a day and 30 days. So it's just the right order of magnitude. It's not 1 year, it's not 10 seconds, but it's still very weakly informative. After we've done that, we can try again to fit our model to our data, and still no luck. We have made some progress because if you look at chain 1, 3, and 4, we can see that when we do a posterior predictive check, it seems to be fitting the data quite well. But we see that chain 2 is still quite off. And we can see that for some parameters like A, chain 2 is not exploring the same region of the parameter space. So we want to dig a little bit deeper. So we plot the inferred posterior distribution for parameter A for chain 2. And so again, A is the inverse of the mean incubation time. So this posterior distribution would mean that almost all probability mass is on incubation time smaller than 1 day, because all of these values are more than 1. It means that the model infers that the incubation time should be less than 1 day, which seems very, very short. So this is a typical case where we put a weakly informative prior on some parameters because it's quick, but then we see that the model infer absurd value. So it means that we haven't put all our prior information into the model. So now is a good time to think a little harder and try to see if we can come up with a more informative prior. So we dug a little bit in the literature available at this time, and we found that typically the incubation time for COVID-19 was estimated at something like 5 or 6 days. So we put a new prior, a more informative prior, this time on the inverse of A, so directly on the incubation time, as a normal distribution of mean 6 and standard deviation 1. So it means like that 85% of the probability mass is between 4 days and 8 days, which is much more informative than what we did before. So this should help the model produce better prediction and also help the inference engine to converge faster. So, but again, when we run the model, we still have Stan warnings. So our hat is still above 1, so we still don't have convergence. So why is that? Actually, if we go back just a few slides, we can see that A was not the only parameters which seemed problematic. Because if you look at P reported, first there is different values inferred by different chains, but most importantly, all chains are inferring values which are below 1%. So it means that the model is inferring that the probability of being reported as a COVID case, if you're infected, is less than 1%, which seems quite low. And so now we have to think, why is the model finding such low values? And if we go back to the definition of the SEIR model, we can see that actually the only way for this model to make case decrease, so to make sense of the decrease we see in the data, transmission decrease that we see in the data, is through immunity. The only way for transmission to decrease according to our current model is that enough people are infected that immunity makes transmission decrease. So that we have understand why the model is inferring values that seems absurd to us, we can understand what is missing in the model, and it's the fact that Switzerland has made some control measures to control the transmission of the coronavirus, and this needs to be included into the model. So to model these control measures, we know that the lockdown has been put in place in March. So we'll parameterize beta. So again, beta is the parameters in the model which control the strength of the transmission of the virus. And we parameterize beta by t the time through a logistic function which model the decrease of transmission due to control measures. And so we parameterize this logistic function by 3 parameters, which control either the delay from the announcement of the measures to the application of these measures, the decrease due to these measures, and how fast this, the decrease is happening. And we just put weekly informative priors on these parameters. For instance, for Xi, we put a uniform 0.5, 1.5, which just means that our prior is that the slope has to be positive, that we expect the control measure to decrease transmission and not to increase them. Yes. So yes, just for the interpretation, this is modeling the control measures, but it's actually can be seen as the influence of the combination of mandatory behavior change and also voluntary behavior change. And so with this new part of the model, we fit it again to our data, and it fit better than before, but we're still not happy because we're still, our at is still above 1, so we still don't have a convergence. So this is another diagnostic plot that can be quite useful. It's a pair plot. So this means that for each pair of parameters, we look at the joint distribution, the joint posterior distribution inferred by the model. So on this plot, we can make several observations. First, we can see that there are some tight dependency between some parameters like beta and gamma, and some really weirdly shaped dependency, like for instance, between P reported and nu, for instance. This could mean that there is some kind of degeneracy in the model, like that some combination of parameters can explain the data as well. Like you can change one parameters and the other while still explaining the data as well. Something else that we can observe is that the posterior distribution for eta, nu, and xi, which are the parameters which control the transmission decrease due to the lockdown, are very similar to the prior distributions, which means that it seems that these parameters are not really informed by the data. The last observation is that P reported, so the probability of being reported if you're infected, is still very, very low, so still below 1%. So why is this happening? We can hypothesize that we have actually some kind of degeneracy between the two ways of making transmission decrease, because the model can make transmission decrease either through immunity or through the control measures. And we cannot prove it just looking at this plot, but we can hypothesize that maybe the model cannot know how to weight these two possible explanations to make case decrease. So we have to explore a large parameter space, which corresponds to all the combination of transmission decrease due to the control measure and to immunity. So this means that we have to add more information into our model. We have to add the information that the probability of being reported is not so low. So they would tell the model that probably the cases are decreasing mostly due to the control measures and the behavior changes. So to incorporate this information into our model, we could put a more informative priors on the probability of being reported. But here we'll take a different approach. We'll just use an additional source of data because we have access to data from serological surveys. So in Geneva, in May from 4th to the 7th, they have tested some people and checked if they had antibodies for COVID-19. So we want to add this source of data to inform our model on the real prevalence of COVID-19. So to incorporate this data, we have to make several assumptions. The first one is very strong one, too strong one, is that Geneva is representative of the population of Switzerland. And the other one is that we consider that having antibodies is the same as in our model being in the R compartment, because basically you get COVID antibodies when you're recovered from COVID-19. But then if we make this assumption, adding this new source of data is actually very simple. We just have to add 2 lines of code. So in the transform parameter block, we just create a new parameters, so P infected survey, which is the probability of having antibodies. And at the time of the survey. And to compute it, we just say that it's the proportion of people in the R compartment during this time. So you can see that we take the mean of the 4th dimension of Y. So the 4th dimension of Y is the number of people in the R compartment. We divide it by N, which is the total number of people. So this gives us the proportion of people in the R compartment during the time of the survey. And note that we have these new transform parameters. We can use it in the model block to create a new likelihood. And so we say that the number of people having antibodies in the survey is sampled from a binomial distribution parameterized by this probability of having antibodies corresponding to the number of people in the R compartment. So this should inform actually the parameters of our model. And using this new source of data, and after some tiny details that I need to skip, we finally arrive to our final model. And here we're very happy because Stan stopped giving us some warning. So this tells us that probably the inference is fine, or actually that it seems to have converged. And if we look at a prior predictive check, we can see that the prediction of the model match quite well the true data. So the prediction is in yellow, the true data are in white. And once we have a model that we're satisfied with, we can start looking at values of parameters. For instance, we can look at the value of R0. So the model infers that R0 was above 3 before the lockdown and becomes below 1 after maybe like half a month after the lockdown. So this is we can analyze the value of the parameters inferred by the model. We can also, another interesting thing is to compare the prior distribution of some parameters to the posterior distribution of these parameters. For instance, we can see that P reported is very informed by the data, probably by the serological data. And for instance, look at the A parameters, which is the inverse of the incubation time. We can see that the model infers, after seeing the data, that it must be below 1/2, meaning that after seeing the data, the model infers that the incubation time should be above 2 days. Of course, we could improve the model a lot. This is just a didactic example, but it's still a reasonable model. And so to conclude, by building this model step by step, I think it has allowed us to understand the building blocks of the model better, to understand the failure mode better. It's also useful to know when you can get away by adding few information into the model, like for instance, a weekly informative prior, and when you need to make more research and put more information into the prior. And finally, it's also useful for transparency, because if you share the early version of your model, it can help the readers to understand how each building block influence the predictions of the model. And to give more general conclusion on the whole talk, is that it can be important to develop model which corresponds to data generating mechanism, which are not just curve fitting, and this can give you some insights on the transmission mechanism. And that Bayesian inference is a good way to propagate uncertainty from our data and our priors into results and forecasts. And that the Bayesian workflow can help us to examine our assumption and our modeling process, and can help to be transparent if we share the Stan code and the different version of the Stan code. And so just to finish, you can try this yourself on our GitHub. There is a notebook that you can run step by step. And in our article, you'll also find a part on scaling up models if you want to build more complicated models with more data and more parameters while keeping it fast. But if you have a question on this, Charles can also answer this question right now, I think. Thank you for your attention.
So yeah, thank you very much for this very amazing talk. I think there are many things that we can discuss. So let's open the floor for questions. So you can use either the chat or the raise hand function. So Mauricio.
Yeah, hello. Well, first of all, thank you for the really nice presentation. Among the last slides that Léo showed, you said that maybe that one in the future can extend the model to be applied in different locations, like to stratify it. So that would mean to come up with a hierarchical ODE model. So you could start with hyper priors, and then my following up question would be that if that's the case, would be an issue the center parametrization of the priors, and the non-centering parametrization would be the same as the lots of examples that are out there, including the Stan manual.
Yeah, I think we can build a hierarchical model. I think actually Julien has stratified his model by location in other contexts, maybe.
Yes, I did a model like that for HIV in Africa, just modeling the resistance. It was not just an epidemic, it was the growth of resistance to anti-HIV treatment. And there was like a hierarchical part in it, yeah. No, it's doable, yeah. And you can also use this, how is it called, Charles? The thing when you can share MPI, right? You can like basically parallelize the ODE solving in every country in my case, and then have like this MPI thing that allows you to share information across chains. That was really cool, actually. I can find the link for you if you're interested. It's published somewhere.
Lisa, your group did fit a hierarchical model to COVID-19 with SIR, right?
It's not SIR, no. So the group I am part of now, currently at Imperial, they use branching processes. So it's not ODE based. Well, it has linked to ODEs, but the way it's formalized as a model, it's not an ODE.
Okay. I was under the impression, so maybe I'm thinking of another model, but I feel like there's definitely an ODE-based hierarchical model from COVID-19 that uses MPI. That's out there, but I'd have to find the reference. And then maybe Mauricio. So yeah, the non-centered or centered parameterization, that's always something to potentially worry about in a hierarchical model. But okay.
Any follow-up questions, Mauricio, or any further questions?
I have an extra question. Sorry for extending this much, but about these new solvers that Stan has, are they only available for the CMD Stan command line? How, like, are they better than the ones that already are in RStan?
Yeah, so you know, when something is available in Stan, in theory, it becomes available in all its interfaces. Now, the unfortunate reality is that RStan is lagging behind a few releases. And the reason why that is because RStan lives on CRAN, which makes it easy to download R packages, but they have a lot of additional testing requirements, which frankly, I don't think are always sensible and which create a lot of overhead. So now the package I recommend everyone to switch to is, so yeah, the command Stan line is a bit difficult to use. However, there is a new package called command Stan R, which honestly, I think it's just as good as RStan. It's much more lightweight, and it's always up to date with the latest release of Stan, right? Then you can combine that with, there's an R package called posterior, which allows you to do a lot of the diagnostics that you would use with RStan. So both of these packages are maintained by Stan developers, and this is really the direction into which we're transitioning. So I do encourage, I don't think the learning curve is very hard, especially if you're already familiar with RStan. Now, regarding the new differential equation solvers, in some sense, they're the same differential equation solvers, right? So the main solvers that we have is we have an ODE solver for non-stiff differential equations and one for stiff differential equations. And then there's kind of add-ons, which falls in between. What's new about these differential equation solvers is they use basically the function signature that Lisa discussed is less strict, right? So it kind of used to be that, okay, you need to specify a function in the functions block that returns the derivative of the solution to your ODE. And it has to take in one vector of parameters, one vector of integers, one vector, right? So it was a little bit constrained. So this constraint has been removed, right? So it's more an API thing. Right? The more substantial change, and that's from an algorithmic perspective, isn't per se the ODE integrator itself, but the method that is used to propagate derivatives through differential equations, right? So what do we mean by that? Stan uses gradient-based algorithms, right? Notably Hamiltonian Monte Carlo. So I need to compute the gradient of my log posterior, right? Which it turns out is the gradient of my log prior plus the gradient of my log likelihood. Right? You can work that out to convince yourself. And so I need a way, you know, so if the computation of my likelihood involves solving an ODE, I need a way to propagate derivatives through that solution. And so that gets into a really cool topic, which is the application of automatic differentiation to implicit functions. But basically, Stan now has, instead of only supporting one differentiation method, which it used to do, it now supports two differentiation methods. And unfortunately, there's not one method that's clearly better than the other. The difference is a little bit subtle, but the kind of the high idea is you have one method, which is called the forward method, which doesn't scale very well when your system of ODE is very large and when you have a lot of parameters, right? But there isn't a lot of overhead cost. And then the other method is the adjoint method. So if you follow a little bit the machine learning literature, this is what they use to fit neural ODEs, right? And the adjoint method has much better scalability with the size of the ODE and the number of parameters, right? However, for ODE systems that are moderately large, the overhead cost is so large that you don't get any speed up, right? And also it's a bit less stable. It's a bit more difficult to tune. So I think it takes more expertise to use. So, we're kind of in a situation where we need to figure out how to, how do we recommend using either method or the other, right? So that's still something we're debating. But the rule of thumb is, when your ODE system is small, the forward method, which is the default method, is going to do better. And then eventually the adjoint method, because of its superior scalability, is going to offer you a speed up. Right? Now, of course, for very large systems, that speed up will be orders of magnitudes.
Thank you. That was a really nice explanation.
Yeah. It's not a simple topic. There's not a simple answer to that, unfortunately. And then there's Adams. I don't know where Adams fits in the picture. I'll be honest. The Adams solver, it's there. No, I'll tell you where the Adams picture solves in the picture. It's because the arcade so the non-stiff solver that we had before did not support the adjoint method, whereas the Adams solver is a non-stiff solver that supports the adjoint method. Right. So yeah, we probably need to clean up the Stan documentation to try and explain all those things.
Great, thank you very much. We're a little bit over time, but if you're okay with it, I don't know if anyone has one last question or something like that.
I do, but I'm not going to ask it.
Yep, go ahead.
No, I'm not going to ask it.
Oh, okay. Sorry.
I have many questions, but I'm not going to. I mean, it's gone on how long? Yeah, it's 1 3/4 hours.
Well, I have one short question, and that is about the priors that you choose. Like if you take a look at, I mean, there's like this very well-known example of logistic regression that if you put like a uninformative prior or like a weakly informative prior over the coefficients, then you get like this very informative effect on it. Like you think it's uninformative, but it's actually very informative. And I was wondering, because we're also discussing about how hard it is to define the priors, if there is something comparable when working with ODEs, if you have had any experience with that.
Yeah, I think it can happen. It had happened in my experience. I think the answer to that is, as Lisa and the others say, it's like the predictive prior check. The prior predictive check. Sorry, it's getting late. Huh? So, and when you do that basically every time, and I do that basically every time, then you see this kind of problems, and you can basically choose a better prior that fits what you want to do. Yeah, I had this problem very recently on another model, and actually it was like some prior that was smaller that was actually better than the flat one. It was really, when you look at them at what you can predict from the model, if you wanted something relatively non-informative, you needed a prior that was really close to 0, which was a bit counterintuitive. So I think that's what you're referring to, right?
You also
Yes, exactly.
one slightly general comment about it. Yeah, so Charles mentioned that when we look at ODEs and parameters live in some space, it becomes messy. And also you would just know from ODEs that so there's a lot of stability issues. So some set of parameters will lead to stable systems, some to unstable, some will lead to chaotic. So there's, yeah, definitely a lot of issues with this. And we do understand, we do have generally some understanding of analytical systems, but only of simple ones, like we know how to analyze linear systems maybe. But when things become non-linear, and this is what most of epidemiological models are, we don't have such powerful analytical tools. So in practice, probably there's nothing better than prior predictors.
Cool, thank you. I think if no one has any very urgent questions, then I say that we can call it a day. And thank you very much for coming today. It was a very, very interesting talk. So it was a bit unfortunate that Meetup broke down while we wanted to start, but I hope that many people have the opportunity to watch it later once we upload it to YouTube. So thank you for coming, and yeah, see you around.
Thanks for organizing, Flavio.
Thank you.
And having
Bye-bye.
us.
Thank you.
Okay.
Bye.